Hello everybody, how's everybody doing? Hope everybody is doing great and has been enjoying learning physics. Today's video is going to discuss what is gravitational potential and what is gravitational potential energy. It's exciting to know how hard, how fast should you throw an object from the surface of the earth so that it never returns. This is something that we are going to discuss as a part of today's video as well. So let us look at what is gravitational potential. Let's begin. Gravitational potential states that gravitational potential at a point is defined as the amount of work done in moving a unit mass from infinity to that point, and it's the negative of the work done. And it's quite written here. The gravitational potential at a point is defined as the negative of the work done in moving a unit mass from infinity to that point. Let's try and understand why this statement says negative. It's a very important concept to grasp, without which it would be very difficult for you to solve problems relating to potential and different other things, that the different other scenarios where you will be using gravitational potential as such. So let's begin and try and understand what it is. Let's say that we have an object out here. The object has a mass capital M, and here is a point P. Let's assume that we have this particular point at a distance R from here, from the center of that mass. We want to calculate the gravitational potential at that point due to this mass capital M. Now, how would you do that? For that, let's say at infinity, very far away place, I have a 1 kg mass. That's a 1 kg mass. Because it is at infinity, it is not experiencing any force because of capital M. It's very far away. You give it a negligible nudge, just that, and slowly it starts moving towards the capital M. As and when it goes closer and closer to capital M, it starts picking speed. And by the time it reaches point P, it has gained a considerable speed. So the body, which is 1 kg, is now at point P and is moving with some speed V. If it has speed, it has kinetic energy, my dear friends. You all know that kinetic energy is half mv square. Now, where did this kinetic energy come from? This kinetic energy comes because it had gravitational potential energy. In the course of it moving from here, from infinity to point P, it converted a part of gravitational potential energy it had into kinetic energy. And this kinetic energy is what the 1 kg mass has at this point. So you all agree with me that whatever is the kinetic energy gained is that potential energy lost. The amount of potential energy lost by 1 kg mass when it reaches this point is the gravitational potential at that point. Right? So, whatever is the potential energy that 1 kg mass loses to come here from when it starts from infinity is what is called gravitational potential at that point. Now, having understood this, my dear friends, you need to understand that the amount of energy possessed by that 1 kg mass at infinity was zero. The reason why it was zero is because, number one, at infinity when it wasn't moving. I only give it a tiny nudge to make it move, and that too very negligible. You can say that its energy practically is zero. The kinetic energy. The potential energy also is zero, because it is not under the action of any force for that matter. So it is not being pulled by any object because this is too far away. It was at infinity. It's only when it got closer and closer and closer did it start attracting, and then it gained kinetic energy because of that. So we understand that there it neither had kinetic energy nor did it have potential energy. So the total energy was always zero at that point. So the potential energy now reduced and it became kinetic energy. That means the potential energy of that mass has gone below zero. That's why the definition says negative of the work done, because the potential energy was already of that 1 kg mass zero. It has lost further to gain kinetic energy. Anything that goes below zero, potential energy has gone below zero, and that's why it's negative. Having said this, let me say what I just said a while ago. The potential energy lost by 1 kg mass alone is what is gravitational potential. If it is 2 kg mass, it would be twice this. If it is 3 kg mass, it's thrice this. So the amount of gravitational potential energy of any object at point P of mass m would be m times gravitational potential at that point, because gravitational potential is only for 1 kg mass. If you get 2 kg mass, it would lose twice the energy. So that's why m into v is anyway negative. So gravitational potential energy is always negative. Gravitational potential energy is always negative. Now I want that statement to sink through. Well, having shared this idea with you, which is a very fundamental idea, without which any potential question that you solve would be meaningless, let's head further and try to get an expression for potential due to gravitation. Let's begin. Well, let's say I have a mass here and the center of the mass is at this point. I am interested in calculating the gravitational potential at a point here. Gravitational potential at a point here. Let me call that point P. The gravitational potential at that point is because of mass capital M. This is capital M. So how do you get the gravitational potential at this point? You will have to get 1 kg mass from infinity, unit mass, which is 1 kg. From infinity to this point, during that course, I have brought the mass up till here. So, just talking about distances, the mass m is at a distance, let's say r, from point P, and vice versa. The point P is at a distance r from m, and this is a point, let's say Q, and that's exactly where I have brought my 1 kg mass. It's on the way to reach point P. It has been traveling from infinity and its aim is to get to point P. So let us see how it's moving right now. The gravitational force on the object is acting in this direction. That's the direction in which gravitational force is acting. And you can also say that the displacement also is in the same direction. Displacement also is in the same direction. Both force is in this direction because it's a 1 kg mass, it's being attracted by this. So force is in that direction. Let me write that F, vector F. And the displacement is dx. It's a tiny displacement it's having right now. We are just looking at the mass moving by a very small amount dx, and it has progressed in the direction of force. Let's assume that the distance between the mass capital M and the place where the 1 kg mass currently is x, and that's how this can be written dx. Well, having said that, you can now calculate the amount of work done. The tiny amount of work done is dw. In moving it by an amount dx, the work done is defined as the dot product of force and displacement. So it is F dot dx. If you just put if you just see what is the angle between force and displacement, because dot product says magnitude of F into magnitude of dx into cos of the angle between them. The angle between force and displacement, my dear friends, is 0 degree. So I shall write cos 0. Cos 0 is anyway 1. So the amount of work done in moving that mass by an amount dx is F into dx. But the question is, what is F? F is the gravitational force between the mass capital M and the 1 kg mass. Well, the gravitational force is given by G capital M into small m, which is 1 kg, divided by square of the distance between them. Currently the distance is x, so x square. That's the force. If you just substitute it there, you will get dw being equal to G capital M divided by x squared multiplied by dx. That's what is dw. Once you know what is dw, you know how to calculate the gravitational potential, because gravitational potential V is defined as the total amount of work done in moving that 1 kg mass from infinity to that point. The point is at a distance r. Before the distance was infinity, now the distance is r, so you can integrate this bit. Let's do the integration. Quite easier thing to do. G and M are constants. They will stay outside the integral, and inside the integral you have 1 by x square dx, and it's from infinity and r. So V equal to G M. What's integral of 1 by x square? Anybody would say that it is minus 1 by x. It has to be evaluated between the limits infinity and r. So V is minus Gm into, substitute the upper limit, it's 1 by r, and the lower limit, it's infinity. So we have 1 by r minus 1 by infinity. 1 by infinity anyway is 0. So we have an equation here, minus Gm divided by r. Now that's exactly what is the potential. The potential can be now written. Let me write the potential here. Okay. All right. I just want to write it once for happiness. So V equal to minus, there is an R here, so minus G capital M divided by R. This is the grand equation for calculation of gravitational potential. You defined it as the negative, and that's why it's the negative that has come up here as well. So having understood this particular derivation, I always stick to doing this particular job, which is deriving the equation, because unless you know how do you get that equation, you will not be confident applying those formulae at different places. So I insist on conceptual understanding. Going further, we have a question based on this. If a mass m, if mass of the earth is capital M, the radius is r, gravitational constant is g, then the work done to take 1 kg mass from the surface of the earth to infinity would be. Now that's the question to you. So here we have, let's say, the earth. Let's try and understand how to solve this question from the knowledge that we have just now gained. Let me color it blue so that it looks at least a little bit like the earth. Now that's the center of the earth. There is a body on the surface of the earth. Question says, what is the amount of work done in moving a body from the earth's surface to infinity? Maybe just to be a little more visual about how we are moving, I'll just say that we are standing here right now. And it's a 1 kg body, so the 1 kg body is here. Well, the radius of the earth, which is the distance from here to here, let's say, is r. The radius, let's say, is r. If you ask me, sir, what is the gravitational potential at that place, I would simply write that U equal to minus G m small m divided by r, because r is the distance from the center to the surface. You would be wondering, in the previous slide, sir, you said that I'm sorry. Yeah, in the previous slide, you said that the gravitational potential is V equal to Gm by R. How did you even arrive at that formula? Arrived at that formula using this understanding. If you know the gravitational potential at any point, you multiply the mass which is placed at that point with the gravitational potential, you get the potential energy of that mass. That is the understanding. When we get this bit, we can now apply the same formula here. So gravitational potential is V and the 1 kg mass is m. Mass multiplied by gravitational potential is gravitational potential energy. Having said that, let us now write down the substitution part. Of course, m, my dear friends, is 1 kg. So we have minus G capital M divided by capital M divided by R. That is the potential energy. By the way, this is the initial potential energy. This is the initial potential energy. So let me write that UI. This is UI. That's the initial potential energy. The final potential energy is what we have to talk about, and we somehow know the answer because we have discussed it a couple of seconds ago. We want to get it to infinity, and we don't want the mass to be moving because the question doesn't say it has to be moving. So when you go to infinity, we have already said that any mass, when it's not moving at infinity and it's not under the action of any other force, then the potential energy of the body is still zero. Kinetic energy is zero, potential energy is zero, total energy is zero. So the final energy, which is sum of kinetic and total, kinetic and potential, is also zero. The work done becomes equal to change in potential energy. Work done, change in potential energy, is final potential energy, which is zero, minus the initial potential energy, which is G capital M divided by R, with a minus sign because the initial itself has a minus sign, final minus initial. So we have W becoming equal to G capital M divided by R. That is the amount of work done, and that matches with option B, by the way. So option B is the correct answer. That's how you get to the answers, the fundamental understanding. Let's move to the next question, by the way. Okay. All right. Let's move to this question. A body of mass m is taken from the Earth's surface to the height equal to twice the radius of the Earth. The change in potential energy of the body will be. What will be the change in potential energy of the body? Let's find out. This was the question in NEET 2013. But anyway, going further, let's talk about it. Here is Earth. So that's the Earth. And at the surface of the Earth, you have a body. At the surface of the Earth, you have a body of mass m. And the mass of the Earth itself is capital M, by the way, needless to say. So you are taking it to a height. You are taking it to a height of twice the radius. So maybe this much is R. You can write that this is R. But you are going to a new height. The new height, my dear friends, is here. And that's essentially 2R, the question says. 2R. What will be the gravitational potential energy of the body? Exactly the same process like how we did in the previous question, but then that was infinity. This is a different point. Let's handle this. The initial potential energy of the body now is G into mass of the Earth multiplied by mass of the object divided by R with a negative sign, R, because the initial distance between the center of the Earth and the mass is the radius itself. How do you write the final potential energy of the body? Because we need to find the change in potential energy. Let's find the final potential energy. The final potential energy is a similar equation, G capital M, because the mass now has moved to a height 2R, and the potential energy has to be discussed between the mass of the Earth and mass of the object of small m. Now, what's the distance between the two? Distance between the two is the distance between the center of the Earth and the mass. the same as in the previous case. Before it was r, now that r has become this distance, which is 2r plus r, 3r. So 3r is the final potential energy. If now you want to calculate the work done would be equal to change in potential energy. The change in potential energy is final minus initial. Final is minus g m divided by 3r. Minus of minus becomes plus into g capital M small m divided by r. So all you will have is 1 minus 1 by 3, which is 2g capital M small m divided by 3r. This is the answer you get, but then you have to express it in terms of small g. Small g is acceleration due to gravity. You must have watched the previous video, and I have discussed with you how to calculate acceleration due to gravity, and one of the equations that described it was, if you just multiply and divide by r square, you have a gm by r square. Gm by r square is exactly what is acceleration due to gravity. So the work done can be written as 2 divided by 3. Gm by r square is small g. There is a mass m here and there is the radius r. So we have w is equal to 2 divided by 3 m into g into r. 2 by 3 mgr is option C. That's how you crack the question. Anyway, going further, let's look at another question here. Two small and heavy spheres, each of mass capital M, are placed at a distance apart r apart on a horizontal surface. The gravitational potential at the midpoint on the line joining the centers of the sphere is. Now, I put this question to demonstrate to you how potentials add up. Potentials are scalar quantity and they add up like numbers. So let us crack this question. Let's see how we do it. Well, my dear friends, let's assume that we have a horizontal floor. So here is a horizontal floor, and let's say I have the first body here. The first body is of mass capital M, let's say, right? And we have another body exactly like this one, right? Exactly like this one lying on the floor. The question says that the distance between both of them is r. So all the way from here to here is small r, right? Maybe I'll just make this look a little bigger so that you understand it better. So this is r. We need to find what is the gravitational potential exactly at the center. At this point, you need to find what's the gravitational potential exactly at the center. Now, if you find what is the gravitational potential at the center, by the way, to the center, from here to here, it is r divided by 2, and from here to here also, from here to here also, it's r divided by 2. So the point at which, let's say I name that point P, at which you're trying to find the gravitational potential is exactly at the center at a distance r by 2 from each of the two spheres. So the gravitational potential due to the first sphere, let's say, is U1. This is the first sphere, that's the second sphere. Both of them are of mass m. U1 is equal to minus g capital M divided by half of r, which is r divided by 2, which is going to be 2 times with a negative sign, 2 times g m divided by r. Needless to say, it's the same distance, it's the same mass. This will also produce the same potential at this point. So let me call that U2. That is also minus 2g capital M divided by r. The total potential, I told you, is a scalar quantity. Potentials are always scalar. The total potential, my dear friends, let me call that V, is simply potential due to the first one and potential due to the second one. These are V's. U is usually used for potential energy, but we have to calculate the total potential, so I shall use V. So V1 plus V2, by the way, V1 plus V2 would be minus 4 times, you add both of these, minus 2 gm by r minus 2 gm by r, you have minus 4, minus 2 gm by r and minus 2 gm by r, you have minus 4 gm divided by r. That's the gravitational potential at that place. Let's say if you have an option, looks like it's option D. That's the correct answer. Well, that's how potentials add up. Let's go further. Let's see what we have got to learn. It's escape velocity. Now, escape velocity is the minimum velocity with which you have to project an object from a given point so that it never returns. It escapes the gravitational pull of that planet. And the escape velocity from the surface of the earth. So let's say that you have the earth here, that's the earth, right? And you have an object on the surface of the earth. How fast should you throw it? What is the velocity of the object you should throw? With what velocity you should throw so that it never comes back to the earth? That's the question. That's the question. So having said that, if it has to go away, then you have to throw it at 11.2 kilometer per second. That's the velocity with which you should throw. So if you take an object, you throw it at 11.2 kilometer per second. It's not meter per second, by the way. It's kilometer per second. If you throw it at that speed, it's never going to come back. That's what is called escape velocity. If you want to throw it any faster than that, of course, it will keep going even after it completely escapes the Earth's gravitational pull. But if you throw it exactly at 11.2, it will go very far away, much far away than the Earth's gravitational pull, and finally stop there. That's what 11.2 kilometer per second does to an object. Going further, let's try to get this equation, by the way, before we solve that question. Hey, you know that the radius of the Earth is r. Gravitational potential energy of a mass that is sitting on the Earth's surface is minus g capital M small m divided by r, where r is the radius of the Earth. We are quite well aware of this equation. Now, it's negative of gmm by r. That means this much potential energy is missing from the body when compared to how much it had at infinity. So this is not the potential energy the body has. This is the potential energy the body has lost in the process of getting from infinity to the surface of the Earth. Having understood that, so how do you send it back to infinity? Very simple. Give it exactly the same amount of kinetic energy. It's lost potential energy, it's lost this much potential energy, and it's silently sitting on the Earth's surface because it cannot go anywhere, it's stuck on Earth. But if you give it exactly the same kinetic energy, it will go back to the place where it came from. It came from infinity. If you give it exactly how much it lost, it will go back to where it came from. So the amount of kinetic energy, which is half mv square, you should give to the already existing potential energy, which is m gmm divided by r. The total energy should sum up to 0, because that's exactly what's the energy that it had when it was at infinity. We have discussed about it. So 0 is the potential energy it had when it was at infinity. Having said that, very simple stuff to be done. Just move this to the other side. I have half m v square being equal to g capital M small m divided by r. You see small m gets cancelled and v square becomes equal to 2 times g capital M divided by r, or this simply implies that escape velocity is equal to root of 2 capital G m divided by r, where r is the radius of the planet. If you are talking about the Earth, then it's the radius of the Earth. Well, you can also express that in terms of acceleration due to gravity. You just multiply and divide by an r. If you multiply and divide by an r, you will have v equal to root of 2 g capital M r divided by r square. I just multiplied and divided by an r by an r. You will see that gm by r square is small g, so v becomes equal to root of 2 g r. That's another expression for the same thing. But for you to use this expression, the body must be projected from the surface. For using this equation, r is simply the distance between the center of the planet and the place where the object is, right? Even if the object is somewhere there, you can say that this is the distance. The capital R here will become the small r. So this is actually a bigger, more general an equation. This can be an equation for projection from the surface of the planet. If you just substitute this as 9.81 and that as the radius of the earth, which is 6,400 kilometer, you will see that the escape velocity is 11.2 kilometer per second. But anyway, going further, let us solve a problem based on this. The kinetic energy needed to project a body of mass m from the surface of the earth r or radius r to infinity is, that's the question. Are you very simple here? Well, you know that the escape velocity is simply root of 2gr. We need to calculate the kinetic energy. The kinetic energy is simply half mv square. V is anyway there, so we have half into m into v square would be 2 times g into r. You see, 2 and 2 will get cancelled. The kinetic energy would be m into g into r. So that is the equation for kinetic energy. JE before it was called JE was called AI triple E. That is the question.